Alright, so in this video I'm gonna be explaining another important article for domain adaptation, still in unsupervised setting, but this time it is discriminator-free. There is no discrimination, there is no discriminator network, and we are doing it for image classification. So it is a computer vision task instead of NLP task. It's a multi-label classification. So I'm gonna be explaining this paper in 2024 from Luxembourg. And these are relevant, very important articles that I will explain some of them in future lectures. So in this paper, a discriminator-free adversarial-based unsupervised domain adaptation for multi-label image classification is proposed. Recently, some attempts have been made for introducing adversarial-based unsupervised domain adaptation methods in the context of multi-label image classification. However, these methods, which rely on additional discriminator subnet, present one major shortcoming. The learning of domain invariant feature, as I said, we decouple domain invariant with domain-specific features if you want to have a very good model. The learning of domain invariant, I mean the upper side, this is domain invariant, this is domain specific feature. So we are talking about this one. The learning of domain invariant features may harm their task specific discriminative power, since the classification and discrimination tasks are decoupled. So sometimes you want to have to increase an objective, but you lose the other objective, so it's a trade-off. But here they propose to overcome this issue by introducing a novel, they call it adversarial critic, that is directly deduced from the task-specific classifier. Specifically, a two-component Gaussian mixture model is fitted on the source and target predictions in order to distinguish between two clusters. This allows extracting a Gaussian distribution for each component. The resulting Gaussian distributions are then used for formulating an adversarial loss based on Freccia distance. The proposed method is evaluated on several multi-label image datasets covering 3 different types of domain shift. Of course, domain shift, when we say domain shift, it could be covariate shift, it could be label shift, it could be concept shift, and other things, but these are 3 major things, and sometimes they're coupled, they're hard to distinguish sometimes. So we have feature extractor, the feature extractor, but A is single label. It's A is single label image classifier and uses a softmax to convert the predicted logits into probabilities such that the sum of all class probability is equal to. On the other hand, but B is multi-label, and we use for multi-label, we use sigmoid activation. We don't care about summing to 1 and those things. That's why these sigmoid are very interesting. Even if you remember Word 2vec, we had some problems. One of the methods that we solved was sigmoid. So there are 3 contributions. A novel domain discrepancy for multi-label image classification based on distribution of task-specific classifier predictions. An effective and efficient adversarial unsupervised domain adaptation method for multi-label image classification. But the strategy does not require additional discriminators, so we call it discriminator-free. And they say that because of that, the network size is reduced. So this is a problem formulation that you see we have source and target data set respectively. So these are I stands for here is I's images of target, images of source, and there are labels for target, labels for source. Of course, your target has some labeled data, some unlabeled, so they have to decouple it, and they mean that to achieve. Otherwise, it's not unsupervised; it is supervised, and we know that supervised domain adaptation is not interesting. Everybody knows that this is not a problem. The challenge is unsupervised, or at least semi-supervised domain adaptation. So f sub g extracts d-dimensional f sub g. Here we extract the d-dimensional features, but f sub c predicts the probabilities of object presence. So the model is optimized using classifier loss, such as asymmetric loss, but the adversarial loss is interesting here because P sub S is just distribution of source, P sub T withdraw from P sub T, distribution of the target. But we have an additional, what is F sub D? F sub D here. We have additional discriminator that differentiates between source and target data. So everything is standard, but the motivation is domain discrimination using the distribution of classifier output. The goal is to identify the classes that are present in an image, positive labels, and reject the ones that are not present, the negative labels. Hence, the classifier is expected to output high probability values for positive labels and low probability values for negative ones. So we say Z is a random variable predicted of any class, and P hat is a probability distribution. Theta is being a uniform random. The theta here, you see, this is just a uniform random sampling that returns the predicted probability of a randomly selected class. In general, a well-performing classifier is expected to classify confidently both negative and positive samples. Ideally, this would mean that the probability distribution should be formed by two clusters with low variance in the neighborhood of 0 and 1 respectively, and hence our hypothesis is that a drop in the classifier performance due to domain shift can be reflected in P hat. So Z sub S, Z sub T be a random variable modeling the predicted probability obtained from source and target. So we propose to investigate whether the shift between the source and target is translated in P sub S and P sub T. If a clear difference is observed between them, this would mean that the classifier should be able to discriminate between source and target samples. Thus, this would allow the definition of a suitable critic directly from classifier predictions. To support our claim, we trained a model using label source data without involving the target images. So the classifier probability predictions are usually formed by two cluster with nearly Gaussian distributions. So as you see, it's just a two-component Gaussian mixture model for both source and target. It's a normal distribution conditional. This is the mean and variance of that. So an expectation, this is a framework that we see in machine learning. I've shown you the application of that. I will play this, by the way, EM methods in machine learning, something like this, that I gather all papers about that have used this framework. And it is also related to how brain works. And so it is also a real intelligence. In both source and target domains, we assume that the first component of Gaussian mixture model correspond to clusters, this one, cluster 0, while the second component to cluster 1. However, due to a large number of negative predictions as compared to positive ones, the components tend to be more dominant. So one of them is so huge, the other one is a little bit small. So in fact, in a given image, only few objects are usually present from the total number. So to alleviate this problem, we propose to extract two Gaussian components, ignoring the estimated ways illustrated. So we propose to redefine the adversarial loss by computing a Freccia distance between each pair of source and target components from a given cluster as follows. But now the difference is just the Freccia distance, the distance. So we have modified this adversarial loss. And you know that computed distributions are univariate Gaussians. The Freccia distance between the two distributions, and we call it two Wasserstein distance, is chosen. It can be explicitly computed as follows. So you see such a explicit and beautiful, simple answer. In addition, we compared to the commonly used one Wasserstein distance, it considers second-order moments. Finally, the two Wasserstein distance has been demonstrated to have nicer properties. So let's pick the second Wasserstein because it has continuity, differentiability, for optimizing neural network as compared to other divergences and distances between the two distributions, such as KL. So it's much better than KL divergence and Jensen-Shannon divergence. So this is the overall architecture. We have source images, we have target images, and so we have a classifier here. But our GMM-based critic is using the information, those Z that I was talking about for after classification, that we use it to have a better performance. So we use 3 multi-label aerial image dataset because in their problem they have cross-sensor domain shift. It's one of the domain shifts that they occur. It occurs in computer vision if you want to work with these sort of multi-label datasets. And there is another one, sim-to-real domain shift. This is another dataset, very interesting dataset to investigate the domain gap between real and synthetic scene understanding images. You know, the labeled images is limited and is expensive. That's why people create synthetic images. And it's easier. You know, in computer vision, it's easy to create synthetic images using those adversarial ideas. But in NLP, synthetic sentences, I mean, if you want to use LLM models like ChatGPT and those things, it's still very restricted in comparison to what we do in computer vision. Another data set, cross-weather domain shift. And this is Cityscapes, which introduces for the task of semantic image segmentation. So you see different methods. If you go from different sources to different targets, you get different performance, different accuracies. This is for comparison with state-of-the-art in the number of model parameters. Of course, these parameters, 42 billion parameters, 29 billion parameters. And so this is the qualitative analysis. We have ground truth, for example, chair and bicycle and person. These are ground truth. And we always use ablation study in our article, in the articles, because we want to see what is the significance if we, for example, add some idea, or if you just ignore it and use the traditional methods. And here is interesting. They compare KL divergence with first Wasserstein. And there are many comparisons, and they understood that the second Wasserstein works well. As I said, in terms of continuity, differentiability for learning and those things.